PhD, I did an internship or like a stay, I think it's like a couple of years ago. So again, I usually pretend this slide is to set the notation. Krylov subspace and a regularization term. So I'll start first with Tikhonov because you've seen this already. And again, same slide you've seen before, assuming the same things. I'm assuming I have a partial factorization of A, which is kind of like the core of the Krylov subspace method. And basically at each iteration, I keep updating this partial decomposition of A so that I obtain a matrix whose columns span this particular Krylov subspace. And again, you've seen before, there's different Krylov subspaces. I will not spend a lot of time explaining the differences between them. But I will just like pick a generic one, and you'll either end up using something like GMDRES or SQR, but it doesn't really matter. The important thing here is that we have a partial factorization of A, and we have a basis for our Krylov subspace. And again, we consider an approximation of the solution of our linear inverse ill-post problem to be in the Krylov subspace. So it has to be a linear combination of the columns of this matrix. And again, we can just do the projection step. And that means that at each iteration, so at each iteration, I basically solve a very reduced least squares problem. This is like very computationally efficient. And as my iterations go, my Krylov subspace increases, the iterations get slightly more expensive, but again, like, this is like the number of iterations. So it's still like, we're talking about like very, very, very small problems that we're solving here. Another thing that I think is very relevant about the things that Silvia was talking about is that we can start with our least squares problem, and that's a bit also related to the question you had at the end, right? So we can either regularize first and then project, and we obtain this, or we could project first and then regularize, and then we would like basically be solving exactly the same thing. Now I want to like give another like small detail about this. So again, we're combining two ways of regularizing this problem. So as Silvia was saying, Krylov methods on their own are regularizing, so they have regularizing properties. So the fact that we're like just solving this is already a regularization problem, which acts in a way of, gives a good space for the solution. So it's true that you have this semi-convergence behavior. So a method like this, what it would do, we can imagine it as like, you start solving your solutions, you start like walking towards your like goal, right? Like your right solution. So at the beginning, you start with a subspace that, as it increases, it gives a really good space for the solution. So something that you think, would be suitable for your solution. So like keeps going. And then at some point, you find a really good solution. And then, because this space keeps increasing, eventually it will be the whole space. And then eventually we'll have this semi-convergent behavior. So we'll basically just be solving the unregularized problem, but that's just because our space got too big. So a lot of things that were not that desirable, like started being introduced in our space, which at the beginning had some really nice properties. And on the other hand, we could just like add regularization. And, if we could solve this, which again, usually because in our scenario, we're thinking about large scale problems, we will not be able to directly solve this. But this in itself, without any projection, is a regularization method because we're adding a regularization term which enforces some good solution, some good properties in our solution. And as Silvia was saying, the idea is that we will combine both to get like basically the best of both worlds. So we have, at each iteration, we're still solving a small problem, which is kind of like doubly regularized, if you want. And I think it's really interesting how these two ways of regularizing the problem really go really well with each other. And then you'll see when I talk about flexible Krylov methods, that just becomes very important. So, right, this is the key point of my talk. So why do we need flexible Krylov methods? So let's find a problem that naturally leads us to need these flexible Krylov methods. And this problem, like at least the way I see it, like that the most obvious example is trying to find a solution that is sparse. Right, so just remember that we're like still trying to solve a linear inverse problem. And now we assume that the solution, we know for some reason, like because we know we have this like previous knowledge that X is sparse. And by that, I mean that most of, so if this is an image, what I'm assuming is that most of the pixels are basically 0. And some of them are, you know, like non-zero. So if we take an LP localization term, like we can just to get an heuristic idea of why this works, just think about the 0 norm, which is definitely not a norm, and also is an NP-hard problem which we will not solve. But just think about the 0 norm. So the 0 norm basically just counts the number of pixels that are non-zero. So I'm basically penalizing this number. I'm basically enforcing the solution to have a small number of elements that are non-zero. So that's good. Again, we cannot solve this. So usually we'll take some approximation of that. And you know, there's different choices that one could do. And I think the most used one, and the one I would usually be thinking about when I think about an LP regularization term, is like taking p equal to 1. And the reason for that is because for p smaller than 1, this regularization, this optimization is non-convex. So you know, we will get a solution, but we, you know, it might not be really the one that you're looking for. So if we take p equal to 1, this is like the convex relaxation of this problem. And I will, even if I do everything with generality, I will usually be thinking about p equal to 1. And again, a bit what Sylvia was like, you know, giving a spoiler earlier. I'm thinking about trying to write this new kind of more advanced regularization term still as a Tikhonov term, or like in some ways a Tikhonov form, because I still want basically something that I can rewrite as a big least squares problem, so I can still use Krylov subspace methods and all my projections just work fine. So this is basically related as well to the question you were asking earlier, or like it was asked at the end of the last talk. And I will give the example basically for the one norm, but again, that can be generalized to any p norm. So I have like a one norm, I can basically just define it like that, right? That's just like the definition of a one norm. And the idea is that I want to write it down as a reweighted two norm. So basically the thing you have to do is basically like fill up the gaps, right? So I know that two norm or reweighted two norm is basically a sum of square things. So I can just like rewrite this sum of absolute values as this sum of this sum of squared elements, which then leads to a reweighted two norm with a big diagonal matrix. So right, let's assume we know how to do this. Easy, we understand that there's something that you probably can tell might go wrong already just looking at this. So I've already told you that I'm looking for sparse solutions. So I'm trying to find solutions that have a lot of zeros. And p is 1 or smaller than 1. So if I just think about things that have a lot of zeros here and like p is 1, well, this will basically explode, right? Again, if we look at it from the continuous setting, which might be beneficial if we want to do some convergence analysis, we might want to smooth this out in a way. So you can think about this modification of this weight as thinking we're adding a threshold, so we don't divide by 0, or we're making the whole functional smooth around 0. And then once I have this, you know, I still don't have my Tikhonov problem. So what I want to do is to really rewrite this as a sequence of Tikhonov problems. So if I assume that I have some previous knowledge of the solution, so for example, I've computed the solution before or have an approximation of some kind, I can just take these weights and apply them to the solution that I already have. And again, like now we're just assuming it's like a solution that I already have. And then I can solve this problem here. And if the solution that I've taken before is similar enough, or like it's like a good approximation of the solution, this weight will be a good approximation of the exact weights. And I'm expecting this to be reproducing in a way or be approximating my smoothed version of the L2 LP regularization. Another thing that is important to note is that now, especially in this case. Now this is square, right? It's like quite big, but it's like square. So it's very easy to invert. So the first thing we could think is like, okay, before I've just been talking about Tikhonov problems where there wasn't anything here. So, just to be safe, let's go back to that framework because we understand it better and has like nice computational properties. So what we can do is just do a transformation of the problem. So basically, we can just think about it as like a change of variables. So if I just take my new variable to be this whole thing here, then I can just rewrite this problem in this way. And if you have some experience with the least squares problems, you can already identify these weights here are something, or they look like something called preconditioning. And actually, because this preconditioning actually incorporates some previous information of the solution, because like it's been evaluated in some previous approximation of the solution, or like some approximation of the solution that we thought was good enough. And this is like trying to approximate the actual weights of this reweighted true norm. I can still see that these weights have some information on the solution. So, they're also sometimes called like prior conditioning, because you can do some nice link with Bayesian theory and see that these weights actually incorporate some prior information of the solution. Right, so what do we do with this now, right? I'm still just explaining the framework, but I still haven't gone into, why is this relevant, or why is this related to flexible Krylov methods at all. So the first thing that we could think of if we just want to solve this sequence is just thinking, okay, it's just a sequence of problems. So we can just like solve each of the problems of the sequence. And every time I solve one problem of my sequence, I will obtain one solution. So then I can go and reevaluate my weights with this updated solution. And then I can solve another problem on my sequence. And then, you keep going like that. And you end up in something that's called an inner outer scheme, because you have to solve a full problem every time you get like a new approximation, like a new approximate problem in your sequence. Sorry, I don't know why I'm just like getting confused with the words. Right, so you could do that with Krylov methods, you could do that with anything else. But what is interesting is that like once you see something like that, you can think actually there are some techniques to solve Krylov methods for preconditioned systems. And the only thing that that's kind of different in this case is that this preconditioning changes at each iteration. So if at each iteration we updated these weights, we would have a sequence of problems, so that, instead of a sequence of problems, you can think about it as having like one problem where my precondition changes rather than a sequence of problems. Maybe that's what I want to say. So when you have this scenario, basically you can use flexible Krylov methods, which basically are an extension of Krylov methods that allows for preconditioning that changes the iteration. So very similarly to what we saw before, the main core of the algorithm is basically updating a partial decomposition of A. So again, this is very important because that's what's going to give us our projection. And we still want a matrix whose columns span our Krylov subspace, but now they will span a flexible Krylov subspace. And I'm not going to explain a lot the details of how this flexible, about the actual description of the flexible Krylov subspaces, because it really depends on the choice of Krylov subspace. But what is really relevant is that each of the columns that are incorporated, or like each of the columns of this ZK, which span this flexible Krylov subspace, are now pre-multiplied by these weights. And again, then the projection step is exactly the same thing. So you basically take your solution, you assume that your solution is a linear combination of the columns of this matrix, and then you go to the original problem, substitute your solution, and then you have this least squares problem. And now there's something slightly different from the non-flexible case, which is that now we have like a bit of a problem with our regularization term. So if I really want to keep on solving this, so if I think that at the iteration I will in some way solve this problem here, because I have these weights in my regularization term, and because I'm still projecting this solution, so I'm still assuming that X is a linear combination of ZK. So now I have this like whole bunch of things here, which are not as easy to get rid of as we had it on the non-flexible case. Computationally, this is not too dramatic, because if you think about the structure of this thing, you have like a really big diagonal stuff, which we don't care about much. And then we have something that's very tall and skinny. So multiplying this diagonal stuff with tall and skinny is not too bad. And tall and skinny, you can do a QR decomposition, which is also not very expensive. So it's not a massive burden to keep this regression term here, as long as you keep the projection. And yeah, again, just to draw a bit more of a parallelism with a non-flexible case, I can show you exactly the same diagram. So I start with my least squares problem, and I can, this is slightly more confusing because it's like a whole sequence, but like assume at each iteration I have this regularized problem, and then I can project it, or I could project first and then regularize, and now these two guys are not the same anymore. Again, like these things here are not, they don't have orthogonal columns, which is still interesting. And I really want to say that, there is no right or wrong path. They're both regularizing, like, because I was saying before that this is a kind of doubly regularized scheme where the space that you're giving already gives regularization, especially if you stop early, or basically if you stop early. And the regularization term gives you regularization in another way. Even if you don't go past this line, so if you just do regularization by adding a regularization term, or if you just project in your flexible Krylov method, in flexible Krylov subspace, you are still regularizing the problem, and you're still adding some information about the sparsity of the solution in this case. But we have to be careful knowing exactly what we're solving, because this would call maybe like the hybrid case, where we're just like regularizing for the coefficients. So we're like projecting on the flexible Krylov subspace and then adding regularization. We'll be solving, in the long run, a very different, or we'll be converging to a very different solution if we don't stop the iteration early. So now let me give you an example, which is slightly different, but I just love these slides, so I'll just try to put them every time I can. I basically want to convince you that this idea of adding flexible Krylov spaces is important. So you could basically just tell me, oh, what are you doing this projection? Like, why don't you just project in a normal Krylov subspace and then still add this related stuff here? And I want to try to explain why I think that incorporating information in the solution subspace is still cool, even if you're like still keeping a regularization term, which, it asks for sparsity in the solution. So, because it looks nicer, I'll just go to a slightly different example. And again, if that's confusing, just ask or just disconnect for a bit. So now I'll be thinking about something like a slightly different regularization term. So I want to use a total variation regularization term, which basically what it will do is to force or like enhance or kind of help the solutions to have like kind of piecewise behavior. So things like signs are good, it like really helps recovering the edges. And the way we define this thing actually is just the one norm of a discrete derivative operator of the solution. So if you think about it, you're still basically solving a one norm of this like a derivative operator in a minute. So Again, like just really please remember these, like these quotation marks. It's not as straightforward as I'm going to paint it now, because you still have this discrete derivative operator in the middle, which has been absorbed in this very kind of heuristic example by the weights, but that will mean that these things are not completely square, and you have to do a lot of other stuff to, like computationally, you have to like work a bit more as well to solve these problems. But I want to show you, like the idea is kind of the same, like I end up having some weights that I incorporate in some space in some way. And I just want to show you how that affects the space. So I have this exact image, the blue one, and I have some corrupted version of it. And I want to obtain a reconstruction of the exact one, right? So I use different things. So just like for comparison, again, these are just the two main important things. If I just use GMRES, so I basically use, my Krylov subspace without any flexibility, and I just look at the basis vectors. And again, these are just the basic vector. I'm not saying anything about the reconstruction. Like I don't want to spend time on that. But if I just look at the basis vectors of my standard GMRES, I have the first one that looks kind of okay-ish, like it's a bit smooth, but like still seems a bit like looks a bit like the corrupted or the exact image. But then if you keep looking at the other basis vectors, I mean, they look super oscillatory, which makes sense because you're like trying to recover something that has very sharp edges, which is like hard to recover with smooth things. But it's kind of intuitive to think that if you want to recover a solution that looks piecewise constant, this one with some basis vectors that look like that, you'll have a problem. Like it'll be hard. On the other hand, if you add some flexibility, and again, I just wanted to focus on this one here because the one I mainly care about. This one is a Krylov subspace that is flexible and has incorporated some information about these edges, if you want, in the solution. So these are the basis vectors. So of course, I would think that if we want to recover an exact signal that looks like this one, having a basis vector looks like that will make things so much easier. Like you might have to add some regularization on top, maybe, but you're already in such a much better position. I think I'm running out of time, so I'll just show you a couple of examples that are unrelated to the TV stuff, and they're going back to just using one norm in this case. So trying to find sparse solutions. So as you can see, this solution is very sparse. There's like a bunch of zeros and there's like some little ones that you can like barely see, some like little stars. This thing has been blurred. And we basically use these iteratively weighted flexible Krylov methods to obtain an approximation of the solution. And these are just some like error plots, quite standard. Yes, our method works quite well. If you compare it with other methods, that's more or less the job, really nice. But what I really want you to focus about, and again, this is just like, some checking things are working, is, and again, like 1 minute and then I'll be done, is that if I use the same technique to choose my population parameter, which is something I really haven't talked about at all, but Sylvia gave a bit of an introduction earlier. There's different ways of choosing your regularization parameter. And I'll choose it in the same way, let's say, like using the same method, which is the discrepancy principle, but again, it's not that important. What I end up saying is that this blue dark line is our method. So it's like, again, coherent with other classical or like kind of already done in the literature problems, so that's nice. But if we look at this like purple line, and this purple line was just like going the other way in that diagram. So when like we are like projecting first and then regularizing. And then we're choosing a regularization parameter for that problem. So the one that's been projected first and then regularized. And then you can see that the regularization parameter that you end up choosing is very different, which I think, well, when I saw it, I thought was quite cool, because then the reconstructions don't look that different. Like both are good regularization methods. But then if you look at what the things, like what is actually happening in the codes, you can definitely see that, all these parameters kind of like compensate a bit for what is the problem that you're actually solving. And you can do some playing with it. You can say like, oh, like how low can I go with my p-norm until I get something that looks nasty? And you can see that, because it's a very sparse image, like having a smaller p-norm is usually a good thing. And this is just like some measures of the sparsity that we were like interested in studying at the time. And again, just to show another example, you can also do that in tomography, so you don't need square matrices for these things to work. Again, the errors look nice. And yeah, basically, I've just introduced these two algorithms to compute sparse solutions of large-scale linear response problems. I quite like that they provide a very generalizable framework, which I think is really nice. Like, to me, the main point is that, as I was saying in the final marks, right? Krylov methods are great. They've been working amazing. Tikhonov is great. It's also been working really fine. But if we want to start doing more advanced regularization terms, we can still combine and reuse a lot of the classical techniques and classical understanding that we had of the methods. And again, if you want to get a grant today, if you add data-driven methods, you are far more likely to be successful. So not just because of that, but I think it'd be super interesting to keep exploring ways of combining data-driven regularization with Krylov subspaces, modified Krylov subspaces. So yeah, thank you very much.
Thank you, Malena. Any questions from our audience? We have perhaps time for one question. Okay, perhaps 1.5. I'll ask the first one.
Mm-hmm.
The W matrices, right? For every step. So the W matrices.
Yep.
The WK matrices, right? Yep. So you were picking them at every step. So they were diagonal in every case, right?
Yes.
Right. So they do depend on this parameter tau.
Yes.
Which I suspect you also pick in a different way at every step. So is that tau k, or is it a fixed from the beginning?
So no, in our experiments, we just basically fixed it. We did try different things. It didn't make a massive difference, actually.
Okay.
I think, you just need something that ensures that your functional is smooth around the origin, or, the weights don't explode. But it doesn't make it, it's not very crucial. You can change it quite a lot, and it doesn't make a big influence on the reconstructions.
I see. And of course, you are inverting there, so you want to make sure that this is positive definite anyway. So you are inverting at the last step, right?
Yeah.
Right. Yeah.
But you need them, you need them both actually in this method.
Right.
So you'll end up inverting it and also having it not inverted.
Okay.
So you need to invert it here, and you also need here.